Welcome all. Today we'll be solving what is known as the Buffon's needle problem. Consider a plane with parallel lines spaced evenly apart. Say you drop a needle whose length is no more than the space between the lines onto this plane. Record whether the needle crosses or doesn't cross one of the lines, and continue this experiment many times. The question asks what the probability will be that the needle crosses a line. Not surprisingly, the answer involves pi, and it is a favorite among amateur mathematicians to say that one can approximate pi by dropping needles onto a grid. Understanding why requires some knowledge of probability theory and calculus, so let's get right into it. As with any problem in probability, we should first define a proper sample space for our experiment, then define a convenient random variable to suit our needs, then computing the probability of the event that we wanted to becomes easy as pi. So the sample space in this experiment is the set of all possible states that the needle can be in when it is dropped on this infinite expanse of lines. In this drawing, the bolded lines represent the lines in our grid, and this space between the two dotted lines represent the snapshot I chose of this grid that we can use in our sample space. And here I chose to have one bolded line to be in the middle between, because this segment right here between the two dotted lines we can just copy and paste vertically up and down to get our entire grid. And even more than that, the needle can land anywhere horizontally, so we can just pinpoint it down to one single line here. Now note that two parameters are enough to uniquely determine the state of the needle along this vertical line segment. First, we can say that the center of the needle lands along this line segment to make it easier, and obviously we need to know where that center is along the segment of length 2a. And so we can give it coordinates here to make it easier. Say that the coordinate of this center is some constant, which is the x, and the y, which is p. And p here varies from some length 0 to 2a. We'll define it later. And second, we need to know how the needle is rotated when it lands. And for that, we need an angle. And I'll say that this angle is the angle that the center makes with this horizontal line passing through it and the needle. And I'll call it theta. It will be right here. Now, these two parameters, which vary for some amount, which we'll determine right now, uniquely determine the position of the needle. Now, how should they vary? Well, if we call this point right here C0, where the y-coordinate, or this P, is 0, then we can let P vary from minus a to a. And for the angle needs to vary between 0 and pi if it is defined this way. Because if we go any further than pi, then the needle's position becomes repeated as it was pi radians ago. And so we have basically our sample space. We know that P is on the interval from minus a to a, as we defined it, and theta is on the interval from 0 to pi. And so our sample space is going to be the Cartesian products of these intervals. Now we've basically defined our random variable, and its outcome is this tuple of p theta, where p is the y-coordinate of the center of this needle along the segment, and theta is this angle that the needle makes with the horizontal line. And remember, p ranges from minus a to a, and theta ranges from 0 to pi. And so this set right here, often called the range space, is simply the Cartesian product of these intervals. Since we say the needle is dropped randomly on this grid, we mean that this 2D random variable is uniformly distributed. So for any p and theta, the outcome that they occur is equally probable, basically. And to find the PDF of such a random variable, we have to take 1 and divide it by the area, or the volume, or in general the measure of this range space. In this case, it's just a rectangle, so finding its area will be quite easy. So then note that the PDF of this random variable, which we call x, is going to be a function of p and theta, which will equal 1 over the area of d, which will equal then simply, there's a rectangle, this side length is 2a by taking the difference, and this side length is pi. So it will be equal 1 over 2 pi a. And why is this a PDF? Because if we integrate this, double integrate this across this bounds, across this region, we will get an outcome of 1, which is as it should be for a probability density function. Now to compute the probability of our desired event, that the needle crosses a line, we need to ask, given a fixed theta, for what p will the needle cross the line? And this is actually very simple to answer. Take a look at this picture right here of a needle that crosses the line once at one point. And it has some angle theta, which is known to us, it's fixed, and we want to find this value of p. Well, notice this forms a right triangle where the side length of this vertical side is also equal to p. Remember, the coordinates here is cp, where c is some constant we don't care about. And so, since we know the length of this hypotenuse, because this is the center and we know the needle's length is 2L, this length is going to be just 1L. So we know then that the sine of theta is equal to, by the ratio, p over L. And hence we find p right away, that p is equal to L sine of theta. For this value of p, the needle crosses exactly once. And if p was less than L sine of theta, then it would cross also just once, because the needle would be going down. Now, where does that stop? Well, we can draw a second needle right here with the exact same angle. I guess where should the point be? Probably right here is the center, yeah? And the needle is here. And the angle is also right here. It is the same value of theta. And so the coordinate is going to be c minus p. And so this length is going to be minus p, and this is the same L. And by the same trigonometry, we get that sine of theta is equal to minus p over L, and hence p is equal to minus L sine of theta. These are the points where the needle crosses this line exactly once. And if p is in between these two values, then the needle also crosses once. And if it's outside this range, then it does not cross. And that is exactly what we want. We are now almost done with our problem because we've determined the values of p and theta such that the needle crosses the line, which is exactly what we need. And here they are. If p is between minus L sine of theta and L sine of theta, and theta is between 0 and pi, then the needle will cross the line. And so how do we compute the probability of such an event? Well, this is simply a subset of our range space right here. And to compute its probability, we have to integrate over these bounds of the PDF, the probability density function. That's exactly its purpose. And so we get, finally, that the probability that the needle crosses a line becomes the integral first over theta, so from 0 to pi, and then over p, so from minus L sine of theta to L sine of theta of the PDF, which is 1 over 2 pi a, and then first with respect to p, then with respect to theta. And this is going to be our final probability. This integral is quite simple to do, so I won't show the steps. And so the answer becomes then 2L over pi a. Now how cool is that? So as you can see, that number I showed in the start, which is 2 over pi, that happens when the needle is the same length as the spacing between the lines. In any general case, as we've done anyway, it's going to be this number 2L over pi a. And so you can say that one can approximate pi, say your spacing was 2 and your needle length was 2, or they were the same, then the probability is 2 over pi, so pi equals 2 over the probability. And you can find the probability experimentally by throwing needles and then taking the relative frequency of the needles crossing to the general needles thrown. Albeit it is quite inefficient. Others have done this in the past, but that's not the point of the video today. You can find some really cool videos, I'll link in the description, of computing pi by throwing needles using a program. And so that is it for today's video. As you can see, we solved the problem very efficiently using the proper methods of PDFs and random variables and finding this range for p and theta where they can be. And so it makes it quite proper. I haven't seen this method done in other videos, so that's why I wanted to show it today. And I hope some of you found it quite interesting. And that is it. I will see you in the next video.